our subsea technology. We're going to start on Appendix A. This is 100 pages, so it's going to take quite a few lectures to get through all of Appendix A. As you can see, if you sort of move into page, let's see, yeah, well, the first real page, past the table of contents, past the glossary, and past the applicable standards, then we get to Chapter 1, Introduction. Several places in the text, or at least many places in the text, they will refer to figures. So they say like figure 1.1. And all of those figures are all the way at the back of the appendix. So I would recommend that you find those figures at the back, pull them out, and then you sort of reinsert them where they are more appropriate to have, because it's painful when you're trying to study and reading here. So figure 1.1, then you have to turn a lot of pages and get all the way to the back and then try to find it. So it's a bit easier if you then insert it behind the page where it has referred to the figure. It makes it easier for you later on to figure out stuff. So that's what I've done myself when I've prepared these lectures. As you will see also from the figures, they are not really of high quality. This is, as I said, an old thing. I'm not sure if it's from early 90s or around there. That's when I think this was created. So some of the stuff is a bit outdated. Basically, it's outdated in the fact that they don't really mention all of the possibilities that we have now, that technology has given us after this was created. But I'm going to try to sort of insert that information as we go along. But the basics are still the same, so that we can, even though it's an old text, it's still useful to go through it. So, for Chapter 1, yeah? What? You don't have the Appendix A? Yeah, then we have to check. Is there anybody else that don't have the Appendix A? No, then I'll try to get it printed during the first break here. So I'll go up to the office and print it. So I've noted the two of you that came in now. So yeah. So the first chapter is just an introduction, basically to subsea production systems. And this appendix will both look at a little bit at what happens up on the floating vessels or the rigs. And it will also focus mainly on what happens down at the ocean floor. And a complete subsea production system, it consists of several subsea wells, and they have to be completed. So it's not just to drill a hole and then you can pump up whatever or not really pump it up. You can avoid it from, you can sort of throttle it down so that it won't burst up by itself, because there's a lot of pressure down there. So first off, they drill a lot of holes into the seafloor to try to figure out where the oil is. And when they hit the reservoir, and they have figured out the extents of the reservoir, they drill a lot of wells. And when they figure out which wells they are actually going to use, maybe they won't be able to use any of the wells that they have done to explore the reservoir. They might have to just close up all of those and then create proper wells where they need to extract it. But sometimes they can actually use the ones that they've drilled for exploration also. And then they have to complete them. So they actually have to build something down into the top of the hole, and on top of it they have to place a lot of structures. So it has to be completed in order for it to be a functional well. Sort of an analog we can pull to it is oil rigs on land. You also have to do much the same there, but you have less pressure. You still have a lot of pressure in there, but there's a lot less than is way down deep under the seafloor. So you don't really get. You will get to the point where you have to keep it from bursting out of the well, but you don't get. You won't get completely the same kind of forces as you get subsea. Also in subsea, you have the whole point that it's underwater, so it's pretty difficult to do stuff down there compared to doing things on land. This also has to be controlled, so that's also a part of the subsea production system. It's the control systems that they use to control everything, and that can range from anything from something that is really, really basic and simple, like a direct hydraulic system where they use a hose, a hydraulics hose going to every single component that needs to be controlled, and then they have to operate each one individually. Or they can have computer control systems where they actually just sit in a control room. They have a lot of computers and they start to flip virtual switches on the screens and everything goes automatically. So there's a lot of difference how things are done. Again, up on land, if you're on a land rig, it's a lot easier because then you can actually physically go over there and you can just turn the valves. So you don't really need all of these hefty control systems that you need when you're doing subsea production. And let's see, it's yeah, I had actually gotten a bit further than I thought. So when they are creating these different reservoirs, which they are going to the oil fields that have usually there's a huge reservoir, but there can also be several smaller reservoirs close by. So if you think like deep down, you have the surface of the water, you have the ocean floor, and then you have like deep down here, we have a reservoir that's filled with oil or gas or whatever it is they're getting out of it. And then maybe there you might have a small reservoir out on the side of it, maybe something a bit deeper also. And what they need to figure out is when they're drilling these wells, they can't just put one well straight down into the middle of the big reservoir and figure out that, well, now we're going to get everything from this big reservoir. Because they're not. They're going to get a certain percentage, and if they are only drilling one well into the center of the reservoir, they're going to get a fairly small percentage. If they drill several wells and sort of place it in several parts of the reservoir, maybe even they drill a few wells out here to get these small ones, then they can connect all of this together and send it up top. And then they will get a much higher percentage of the resources that are in the reservoirs. This percentage can also be raised by drilling extra wells. Let's see here. Maybe we put one in here. We drill it down to here, and maybe one out on this side, down to there. And these extra wells will then be used to pump seawater or waste fluid or anything. It's even been experimented with CO2 when it's gas in here, so pumping CO2 in, just to keep the pressure up so that they can get out a higher percentage of what they actually want to get out. But in the end, you will get to a point where there is still resources inside a reservoir, but you don't have the technology to get everything out. And that's when you sort of have an outdated field. It's old. You need to kill off the wells and just leave the entire oil field. But that's usually 30, 40, maybe 50 years into the future after you start developing a field. The problem is, up until 10, 15 years ago, usually this was all done from either a floating vessel up top or from an actual rig that was anchored to the seafloor. Standing on some pylons or anything. But now, as we've gotten along with technology, it's become increasingly deeper and deeper and deeper. The distance from the surface and down gets deeper and deeper, which means that actually using one rig and then drilling what you can from that rig, because if you have this one rig, it can drill down here and it can get at certain angles here, but it can't get further. So that these extra wells here, they can't be made if you're doing everything from the surface. So that's where the subsea industry has come in. So we have been able to create extra points where you can hook up, create more wells, hook up neighboring smaller reservoirs where you might only need one well because it's so small that with one well that will be enough to get most of it out, or at least to get enough resources from that small reservoir to cover the costs of connecting it, and then get some profit from it. And as we have moved along even further with technology, we have gotten to the point where you might just have a ship floating up here. It's either floating using its thrusters to keep its position, so counteracting the wave motions and the wind, or it has actually been anchored with chains to the seafloor so that it's keeping its position. And then all you need is what's called risers, which is the pipes going from a manifold, which is gathering everything from the subsea wells. It's gathering everything into the risers, or into the manifold, and then it sends it through the risers and up to the surface vessel. There were still risers that's being used no matter how you are working, whether it is the platform, the rig that is placed there, or if it's a floating vessel. It's still risers that are used, but often on older rigs they would use more or less one riser per well, so they would go individually down for every one of them. But what's used now with a lot of subsea wells is that they sort of mix them together and then they send them up. And then we've gotten even further. So one of the fields outside of Norway, the Ormen Lange field. Ormen Lange is an old Viking name for a ship, actually. So it's a pretty mythical name. What they've done there is that they've completely eliminated the floating vessel. And instead they are sending everything by pipelines to the shore. So that's up north in Norway, or fairly to the north of Norway, at a place called Aukra. These pipelines come in and they process everything, and then they send it into new pipelines that go along the entire Norwegian coast, more or less, down to around this area, and then they spread it out to the rest of Europe. So there's an enormous amount of kilometers of pipelines there. So it's, we're talking thousands upon thousands of kilometers. So, in other words, if we have shallow waters, fairly shallow waters, we can use the old-fashioned systems with a rig or a floating vessel, drill everything down and just do it the old-fashioned way. But as it gets deeper and deeper, we really need to move down to the subsea solutions and start doing things, more and more things down on the subsea floor. on the seafloor. So the chapter 2, we're still on the first page there. So chapter 2, the applications of subsea completions. So one of the applications is to extend the reach. Like I showed here, we can extend the reach to cover the entire reservoir by using subsea wells to complement it. We can also extend it going out to neighboring reservoirs, which is the 2.2 point there, marginal fields, to sort of hit those smaller ones, which if this one had been alone way out here, it wouldn't have been profitable to connect it, because then you would have needed instead of needing a pipeline from here to here and then drilling a well to get it, you would have needed all of the infrastructure that you have here on top of this very small field. And that wouldn't have been profitable. It would have cost too much money to get the oil out. If money wasn't a hindrance, let's say for some reason all of the oil in the world has been used and we really need everything we can find, then that might be profitable to do it, because then the oil price would shoot up into the sky. But as it is, even with the high oil prices that we had a few years ago, many of these smaller marginal fields would not have been profitable if they were completely on their own. But as soon as they are fairly close to another field, then they can be connected to the infrastructure already there. So then you can actually exploit them. So here we see some of the illustrations. It's the figure 2.1. A little bit of what I've already been drawing. You have a rig on the seafloor. They've drilled a lot of wells, and you can see they can get a certain angle to the wells, but they can't really get it spread all that far when they're going from the same starting point on every one. And what they really want to do, if we see it from the top, so from the top and down, what they really want to do, they want to have one well on each of these points. That's what's the ideal placement of them, because then they will have a good flow on every well, and they will sort of manage to reach all of the outer points of the reservoir, as well as can be done. It's not always all that easy to get it everywhere. I actually know that Statoil has, I think it is in Stavanger, in their offices in Stavanger, they have sort of this huge hall. I think it's actually larger than Auditorium A here. It's even bigger than that. And they have sort of projector screens all around the walls, and they have this huge stuff in the middle that with a lot of cannons to project images. And then they can actually recreate the insides of a reservoir. So when they've done a lot of seismic surveys and stuff, they have sent their sound waves down and they've gotten their echoes back up. They've used this to create 3D models, and then they project it onto the walls. So they can actually get, the planners can actually get a feeling of walking around inside the reservoir, because they're walking around inside this room and they've got all of the walls of the reservoir just everywhere around them. And I know that recently in the last year, I think, I've read a couple of articles about them starting to use VR technology, so VR glasses like Oculus Rift and stuff. So they're starting to use the new technology more and more to do this. And that's, from what I've heard, it's hugely helpful when you are sort of trying to plan exactly where do we need to get all these wells to end up. Because basically, think about it, you're up here, and you're going to control something that's going all the way down here. And that might be, you might have a couple of 100 meters of water, and then you might have almost 1,000 meters of seafloor before you get down to the reservoir. So it's pretty amazing how they actually manage to place these wells. But that's a whole it's a whole technology in itself, a whole educational field in that respect. You actually have your own drilling engineers for that. But the key here is to have the correct spacing between the wells in the reservoir, so that you sort of get an optimal, what should we call it, an optimal draining of the reservoir might be a good analogy. Because the point here is that often if you read newspaper articles and stuff, it says that, well, we are pumping the oil up. But that's not what's happening, because you might have up to 1,000 or 1,500 bars of pressure inside that reservoir. So the whole point is to keep the oil down there until you're ready. So the whole job with all of the infrastructure and all of the pipes and everything is to sort of keep this pressure under control until you're ready to open the valve and slowly let it enter your production facilities. So that's a more correct view of it than actually pumping it up as the newspaper articles usually do. And that's sort of a phrase that's, I know that it's sort of gotten into our languages because you hear me saying it also. We're pumping up the oil, but that's not correct. That's not how it works. We are avoiding it from shooting out at a pretty high speed there. So we are keeping it back, keeping a lid on it, basically. So you also have the one I was talking about here with the marginal fields. You get the field out on the side, so you can use a subsea well to exploit that one. And instead of making all of these tons of wells from one point, you can just add a couple of subsea wells further off. And that will allow you to get a better. So like if this rig was placed on top of here, you can have subsea wells out here to get to this sort of finger in the reservoir. And then you have this subsea well which is doing these wells. Let's see, we have the so you also have the on this one, the previous one, this part here, yeah. It's two different reservoirs, so it's not connected. So no matter how much of the oil you actually get out of this reservoir, you won't be draining anything from that one, unless you get separate wells into this one. So what you do is you create a subsea well, you complete a well on this side, so you drill down into this reservoir, and then you get everything up here, and then you send it by pipelines over here and connect it to the rig. So that's sort of the entire point with those, because most likely between here there will be some kind of rock that is pretty hard and it's not permeable, so that you won't get, there's not, it's called porous, there's not a lot of air bubbles inside it, so the oil cannot travel through it, so it's completely locked off. So that's why you have to have separate wells for that marginal field. And if that marginal field is placed out here instead, so a lot further away, then it might not be profitable. It might be too expensive to connect it to this larger reservoir, and there is too little oil in it to develop it on its own. So it's basically the same one, only here we are talking about more shallow reservoirs. So there's shorter distance between the seafloor and the reservoir, so maybe there's just a couple of 100 meters. And then you have the problem with, as you see here, you're coming from one point and you can get pretty good spread on the wells if the reservoir is pretty deep. But when it's not deep, there is only a certain angle you can get when you're drilling the wells. So then you end up with not having it spread out all that much. So then instead you can put down subsea wells in order to get to these other parts of the reservoir, so that you can get everything out of it. So instead of trying to get everything from the middle, you put subsea wells on the sides also to sort of space it out better. Of course, this is a bit outdated, because I know nowadays they can drill down here, and when they have gotten into the reservoir, they can actually angle it so that it's drilling horizontally. So it's the technology has gotten pretty far since this was made, but still, I know there are sometimes a bit problems with the horizontal wells. I'm not quite sure what it is, but they really don't like using them unless they have to. So if it's going to save them a lot of money creating a horizontal well that goes sort of into this part of the reservoir, instead of creating a subsea well, the subsea well will be actually a lot more expensive than drilling the horizontal well. Then they will of course do the horizontal well. But I know that they've had a bit of problems with them, so I don't think the horizontal drilling technology is quite perfected yet, so that there's a bit of startup issues there sometimes. But I think within 5-10 years, they've probably gotten it perfected so that they can do quite a lot from one point. So how it often looks is, now we can't get everything because of these lights, but basically this is the figure 2.2. You have a shuttle and a storage tanker up here. So one of them is hidden by the lights, the shadow of the lights. But one of them is the tanker, and the other is the storage tanker. This one. So it's getting everything from the pipelines coming up to the ship, and it's storing it. And then you have other shuttle tankers coming in. They are offloading into those, and those are going off to other parts of the world to deliver the oil. But this one is stationary. This one stays here all the time, because it's connected to the production riser, which goes up to it, and the production riser is connected to the manifold, the subsea manifold. So you can see all of these satellite wells, they are sending their production feeds into the subsea manifold, and the subsea manifold is mixing everything and then sending it through the riser. Now what they've started doing a lot of is to actually put a lot of the production equipment that might be on top of that. In this case, it says a storage tanker, so this one is only storing it. So probably this is only crude oil they're getting from this reservoir. But if they had gotten a mixture, oil and gas, from the reservoir, you might actually have separation going on down here. So they might separate it into different flows, sending one flow of gas up, and then through another pipeline, a flow of oil. And you have quite a lot of equipment that they can put down there now to do stuff before it gets up. And what they often do when they are exploring for new reservoirs, so exploration drilling, as it's called, is that they have one of these semi-submersible rigs. So it's called semi-submersible because when it's moving, they've unloaded the ballast so that it rises up, and then they have these two sort of ship parts that are up in the surface of the water, and then they move along that. But when they need to do operations, they want to not be that much affected by waves. So what they do is they fill them up with ballast water so that they sink below the surface. Because what happens is, let me see if I can draw this fairly well. We'll get more detail into it when we get to part 5, I think it is. But we can do just a short one here. So you have the surface of the water. And if you have a ship placed inside the surface of the water, and then you have one of these semi-submersible ones. So the problem with waves is that it's the entire cross-sectional area. So if you could sort of remove, do a cross-section through the entire ship exactly where the water is, exactly where the surface line of the water is, that's the area that's affected by the wave motions. So for a regular ship, that means basically the entire area of the hull is affected by it. But for these semi-submersibles, when they fill up with ballast water and the pontoons end up further beneath the surface, then suddenly the only surface area are these small pylons that go down. So they have a lot less surface area, so that even though there are a lot of waves, it will be more stable in the water. So it will be sort of it won't be that much affected by the waves as a vessel will be. Or a ship, rather. So usually they use these semi-submersible when they're doing exploration drilling and drilling proper wells also, production wells. So they drive them or they transport them to wherever they are supposed to be. Then they fill them up with ballast water so that they are ready, and then they start drilling down at the seafloor. Yeah? What did you mean? Yeah. The pontoons is basically the ships, the part of the hull that is similar to a ship. So that they're just called pontoons because they are floating. What's it called? If you have a floating dock, it has pontoons beneath it because you fill them with air so that they're floating. So that's usually if you are using something to float something else, you call it pontoons. So. Yeah. The ballast is they actually fill them with water. So when they are transporting them, when they are up here, so that this part is up in the surface, then they have pumped all of the water out of them. And then when they need it to be submerged, then they just pump water into these so that they fill it up with water. So then it sits further into the water, and then it starts to sink to a certain point. And that's actually often what they do with vessels also. If they have a huge... have any of you ever seen these oil tankers? How huge they are? They are enormous. And if they've transported their oil to somewhere and offloaded it, then they are suddenly empty. So you have this huge ship, and it's sitting more or less on top of the water instead of sitting fairly deep into the water and being solid there. So what they do then when they are going to send it back, they fill it with some kind of ballast. Now I know that for an oil tanker it's a bit different because they have to use something other than water. They can't just fill the oil tanks with water, because then when they pump the ballast water out again, a lot of oil would follow it. So they have to do a bit of different stuff to manage this. But like for any other cargo vessels also, they usually have water tanks somewhere on the vessel, which they can fill just to get extra weight so that they sit better in the water when they don't have any goods that they are shipping around. So when they are moving a fairly empty ship, they can still get it to sit properly in the water. So that's the whole point with the ballast stuff. It can also bring a lot of problems because they can end up bringing ballast water from a port here in Norway, and they can bring it to South America or something. But then they also, when they are loading more stuff in South America to bring back to Norway, they have to pump some of the ballast water out, or else they will be too heavy. But then they are pumping the water from Norway into the sea outside of South America, and the water in Norway might have different kinds of living animals in it, so tiny marine animals, bacteria and stuff, and so they end up bringing it to other parts of the world. So I know that there's a lot of I can't quite remember what they're called, but there are a lot of clam-type shells that have been brought from, I think it's the coast of Russia, and been brought to the United States. And they have a huge problem now, because now they are completely infested by them, because they don't have any natural enemies in the coastal waters of America. So that these are just spreading out everywhere, and ends up becoming a large problem. So it's something that shipping companies have to keep an eye on, exactly what they do with their ballast water and stuff. So we have the early production systems, which means that sometimes it can be more effective to actually connect an oil field that you are developing. If you can get some subsea wells in there and actually connect them to a neighboring area, like here we have the Oseberg field. This is the Oseberg field. So it's a fairly old field in Norway. You also have it up here. So here you have the Oseberg part. You see here Brage, which is this part. That's this part as well. And then they discovered another reservoir out here, which is the Troll field. And what they ended up doing was, let's see. Yeah, they ended up connecting the Troll field with the Oseberg field, the TOGI, Troll Oseberg gas injection. It is. So they connected these two fields before they got it properly on the way there. Here you see the actual TOGI module, which they put into the Oseberg area. So this is where they connected the pipeline, the TOGI pipeline, into. One of the good things about doing stuff like this, yeah. This one. This one, the whiteboard. Just to point with, but we're getting into more details in this in part 5. So I can't really use all that too much time on it now, because we're going to look more at the whole semi-submersible and floating vessels later on. So one of the good things about being able to connect a couple of fields early on is that you can lower what the oil companies call time to first oil, which means that when they are developing a new field, they might be using 3 years maybe to build everything and get everything into place. But if they already have one of their exploration wells, which they can easily create into a production well, it's well placed and everything, so they can complete it so that it can start producing, and they can connect it to a neighboring field, then they will already start producing stuff. So instead of having to wait several years for everything to be completed on the production facilities on that specific field, you will start producing oil from it very early on. So it's a very, very nice way of sort of making sure that you have a cash flow during the entire project. So time to first oil is something that you will definitely hear again, not only in this course, but you will hear it in the industry in general. It's very important to try to have as short as possible time to first oil. So any sort of tricks you can do to make it faster, make the oil production start up faster, that's good. Because then you will have a trickle of income constantly. Even though it's just a tiny little well that you're sending in here, even though it's just a little bit that you're getting, you're still getting income, you're getting profits from that well, which you can use to pay off your debts and everything to when you are creating the rest of the installation for the large field. So I think we're going to do a break, and I'm going to print Appendix A, and someone was missing part 2 also. That was you, yeah? And I'll print both of them now, just so you get it. Have you looked through it? Is there something else you are missing? We could maybe just look through it now before I... right. Sometimes a subsea well can also be used to run tests on reservoirs, because even though we have a lot of nice analysis equipment and stuff, the seismic gear and everything, we can get to know a lot of what goes on inside a reservoir without actually being inside it, but we can't get to know everything, and some reservoirs are pretty complex. So there's a lot going on in there. So if you can use a subsea well in order to do tests on the production flow coming from the reservoir, so that you can sort of see is there something additional in here? Is it producing sand as well as oil? So are we getting sand that's following the flow of oil out of it? That's going to make a huge problem for our producing equipment, because sand moving at pretty high speeds, high velocities, it's going to work like a grinder inside the pipe. So as soon as you have a bend in the pipe or anything, the sand will hit this wall and it will start grinding it from the inside. So it's going to put a lot of stress on the production equipment. And this is stuff that you can't really know until you start producing it. So if you get a subsea well up and running before the rest of the system, then you can sort of figure out that, whoa, okay, we might need to redesign some of our parts here because we have some extra stuff here that we weren't really aware of that was going to be a problem. So that's a nice way of using such reservoirs also. And then we have deep water systems when we are getting into fairly deep waters. So what is often used is either it's only given as a TLP in the text here, but it's called a tension leg platform. So it's basically a platform just as any other platform, but instead of being placed on top of a rigid structure that is placed on the sea floor, it is floating. So it has these pontoons that are filled with, most likely air, in order to make the entire structure float. And then it has these wires that go down to anchors on the sea floor. And these are tensions. So they are in fact pulling the entire rig a bit deeper than if it was just floating by itself. So that there's a constant tension on these legs here. So they're sort of keeping it in place that way. Another way of using, as I talked about in the deepwater system, is using the floating production facilities. So whether they are only used for storage and then offload onto tankers, or if they are a so-called Fpso, which is a floating production, storage, and offloading unit. Those are the most complex ones. So they are sort of, yeah? What? TLP, it's a tension leg platform. I can write that also. So TLP. Tension leg platform. Which basically just means that the legs of the platform are the wires, and they are under tension. So that's what's keeping it in place. So an FPSO, floating production storage and offloading unit, is basically a very large ship that has usually been rebuilt so that it might have served a purpose as a tanker or some sort of transport ship earlier, but it has been rebuilt and they have placed a lot of production facilities on top of it. So instead of having an entire platform rig, they just have a vessel instead. And usually these vessels, they will of course be subjected to a lot more forces from waves coming on the side than from the front. So what they usually do is that they have some sort of rotating connection below here so that they can actually rotate the entire ship, so that they keep the front of the ship towards the waves at all times. So they keep the bow so that it's cutting through the waves at all times instead of getting waves from the side. And as you can see here, this is a very modern system. So you can see these risers and stuff, they are going sort of looping stuff here. And that's because the ship it's not stationary, it's floating, so it's going to move with the wave, so it's going to move up and down. So you need to have this sort of curve to everything so that it's allowed to move, basically. If it had been connected straight down and into something at the seafloor, you could have risked if you got into a big storm or something, you could have gotten high enough waves that you would actually pull them off. So when you have these systems like this, you get them into get a nice motion on it. So it's not that much stress happening for the pipelines in there. And these are flotation devices, so they're anchored down here, and they are like huge drums that are just floating there. So they are actually able to keep the weight of themselves and the entire pipeline there. So that's a really cool system. That's more how they look nowadays when they create deep water systems. Yeah.
This rotating device under the ship.
Yeah.
Does it have anything to do with dynamic positioning?
Yeah, it has to do with the dynamic positioning because usually these they are kept in place with dynamic positioning, which is we'll get really into detail in it in part 5 when we are talking about vessels. But it is basically a system that combines GPS and a lot of other information that it gets from the waves, wave direction and the force of the waves and everything, the velocities. It combines everything, and it sort of it turns the ship so that the bow is in the correct position, that it is facing the waves, and it also keeps it in place so that if we are getting stronger waves towards it, it will increase the force of the thrusters just to keep in position. So it is constantly counteracting the force of the waves with its thrusters. So it's a pretty cool system to have, and there are several classes of it. So a ship like this needs a very advanced DP system because even though you have room for a lot of movement in these, you can't sort of float 15 meters to the right or something. That's not good. You have to stay more or less in place. So they have really good systems for that. But like smaller vessels might only have the first classification of DP, which basically means that it won't really hold up in worse weather and stuff. So. But these Fpsos usually have top of the line stuff. So in the deep water area still, one way of exploiting reservoirs that are in deep water is to use not so deep water to place the rig on. It's hidden by the shadow, but there is a platform here, and they have extended the pipelines down basically a mountain range that is on the water. So they've placed the pipelines all the way down to deeper waters, and here they have subsea wells that are connected to the platform. So that's another way of doing it. But of course, you need a lot of things to come together here. You need the reservoir has to be fairly close to the not to the more shallow waters, and also you have to have the possibility of actually putting a platform there. It is more usual to use the tension leg platform when you are using it. So then you have a subsea template with, usually if you have a large template like that, you will have several wells inside one structure. So you have maybe 6 or 8 wells, maybe 12 wells drilled through the same one. So they will all be spreading out in different angles to get to different parts of the reservoir, but they are all located very close to each other on the seafloor. Or you can have single wells, satellite wells, that are just placed where they are supposed to be. And they are all connected to a tension leg platform then. But here's where we can see the age of this appendix, because according to the appendix, you will either have to do the floating one, or you will have to do the tension leg one. There is no possibility of sending it directly to shore or anything like we've already done on several systems. So it's sort of it doesn't show the possibilities of today's technology, but it shows the basics of everything, where everything comes from. Chapter 3, approaches to subsea development. So we're going to talk a little about different systems that have been used subsea earlier. I've already mentioned them briefly, some of them. One is the dry system, which I mentioned, where you placed all of the production equipment basically inside a submarine. There was a stationary submarine placed on top of the production equipment. So you could lower down a sort of a diving bell connected to it, and then a person dressed in regular clothes could crawl into it and do all of the work in there, which is a fair enough system. Of course, as you get to deeper and deeper waters, this is going to be a heavier and heavier structure, because it needs to keep all of this hydrostatic pressure outside. So it's going to need to have quite a lot of wall thickness, and it's going to need to be quite strong, but it's not a problem producing something like that, not at all. It might take quite a while to lower the diving bell down to get the person inside, but that's not really a problem either. It takes just as long to lower an ROV down to do some work down there, so that's not really a huge problem either. But there is one thing. Here's the diving bell. So there it is, where it connects to the subsea part, and here the operator sits inside as they are lowering it down. And inside here, it's just like being inside a regular room. Basically, it's regular atmosphere, regular breathing gas and everything. You're breathing regular air pumped down. But the problem is when you get someone into an area like this. This is from I think it's from a land rig. Might be on a platform, but I'm not quite sure. But here they have a blowout when they are drilling a well. So you can see the guys down here, and now it's just. You can see the point with where I'm talking about trying to keep the pressure inside instead of actually pumping out everything. And what if this happened when you had a guy? Let's see. When you had this guy sitting in here working, and you got a blowout inside there, that way he would have been dead in no time. So that's the main reason why they've dropped these kinds of systems. They're not using them anymore for new developments. It's basically because they are afraid that something is going to go wrong down there while you have a person down there. So, and if something happens in here, it's not like having 3 divers outside, because the divers actually have a chance of surviving. So if something goes wrong with one diver, you have 2 other divers there that can actually help him, and you have a chance of getting him. And the divers usually have training in a lot of first aid and sort of basic surgery techniques. I know there are divers that have had to remove their own appendixes inside the diving bells because they were under pressure. So no one could get into them, and they couldn't get out because they had to be depressurized over a week. So they actually had to do operations on themselves. They would, of course, have video conferences with actual surgeons out there guiding them to do everything, but they had to do it themselves. So it's pretty. They can handle pretty rough situations, and of course they would be outside here. They would be out in the water, so a blowout in the water wouldn't be the same problem as inside there. Have a guy in there and you get a blowout, he's dead in no time. The divers actually have a chance of surviving. So, And even better if it was an ROV, because, well, worst case, the ROV is destroyed. So we have to buy a new ROV for a couple of $million. So that's just money. It's not a human life. So. Then you have the wet systems. This is an example of a wet system. So it's placed down on a template. So beforehand, they've completed the well. So they've created sort of a lid for the well. They've created a platform around it to lower the structures down onto and place them on. And then when they come down with this one, this is what is called, this, is it a Christmas tree? Certainly got, yeah, it's a Christmas tree. So they call them Christmas trees because they have valves going in every direction, and they are usually vertical. That's the old part, is that they are vertical. So there are a lot of valves stacked on top of each other. And then if you looked at the Christmas trees that are used on land, it will be placed on top of something, and then you have sort of one part with its valve wheel. Then you have another part, and the valve wheel might be out here. And then you have another part, valve wheel on this side. And then you have more and more valve wheels. So you're sort of just building on it. So it kind of looks like a Christmas tree when you are looking at them. So that's why they are called Christmas trees also. So the basics are that they have a guiding frame, which is used to sort of get it in the correct position when they are lowering it down. There's a lot of valves in here to work with. All of these are hydraulic valves, so they are sort of encapsulated because you have hydraulic systems in there that are using them. So it's not that easy to see it in this one. We will have several figures later on that will show more how the valves look. You have production valves, master valves. Then you have at the top, you have a tree cap all the way at the top there. And that is because sometimes they need to do stuff inside the well. And I've already mentioned the through flow line part, where you can actually pump equipment or tools through the production line and into the tree, so that it can do work down there. And then you will sort of have to calculate, well, how much do we have to pump in order to get it in the correct position for it to do its work. But what is also done is that you can get in another vessel that places itself on top of the or above the well, and they lower down a wireline tool, and then they go in through the tree cap, and then they just open up the valves going all the way in, and then they can lower a tool straight down into it. In the horizontal ones, it's not that easy to go in with wireline tools. So no, in the vertical ones. So now they are moving more and more for horizontal ones, where the valves are placed on a horizontal line instead, because then you have the center opening is completely open, so you can just get into the. It's of course closed with a cap and everything, but you can open it up and send in equipment that you are lowering straight down. So there's a lot of different ways of doing this. This appendix touches briefly on the horizontal ones towards the end. Yeah.
Did you say it's easier to send in equipment into the horizontal ones or the vertical ones?
For the horizontal ones, the ones where they are sort of, instead of stacking the valves on top of each other, they are keeping I'll draw one beside there. They are keeping the middle part more or less free, and then they are doing the valves on the sides instead. So they're building them sort of sideways instead of stacking them on top of each other. because when you stack them on top of each other, it's not enough to just open the lid and then lower something in. You have to sort of remove the valves in order to get inside there. So that's a lot of work. That's why it's often can be cheaper to have a through flow line system if you have an old Christmas tree. So it's easier to get in there with equipment. Here's sort of a I really don't like that shadow up there. If you open up your figure 3.4, you will see up here here's the sea floor. So you have the base here, and then you have the structures up here with the different valves on the Christmas tree and everything coming up here. And here you sort of have a representation of what it looks like down in the hole. So it starts off with having casings that are suspended from the guide base at the bottom here. So the casings go down. Inside the casings you have the tubings, which are basically just pipes going down there. You get to a certain point, and then you get this one, a subsurface safety valve. In this case, it's an easy subsurface safety valve. You actually have some that are called. Let's see if I can get this right. I think it's SCSSV, which is surface controlled subsurface safety valve. It's a pretty heavy expression. This one is shown just as a subsurface safety valve, so it's an old one. It's not controlled from the surface. You don't have any. Well, we will talk about the surface control one later on, but the surface control one has a connecting line up to whatever is up top, if it's a rig or a vessel, where they can actually manually control it. This one is sort of to stop if something happens up here, something wrong happens and you get a leak, this one is supposed to stop the flow. So the subsurface safety valve is supposed to be able to sort of block off the flow until you get equipment in to fix stuff. It doesn't always do that, so you can get. I know that on some fields with especially high pressure, it's been required that they have two subsurface safety valves. So they have one on top of the other in order to have sort of a redundancy, so that if one fails, the other one will try to catch everything and stop it. But it is basically a safety tool in order to avoid a lot of oil spillage to the environment. And then you have further down you have a bit more tubing and casings. You have all the way down you have sleeves, guide nipples, and then you have the production zone, which is basically where when you get down to here, all of the pipes will be perforated. It will have a lot of holes, so that the oil will leak or will be pushed by the pressure from the reservoir walls and into the drilled hole, and then they will flow into the holes in the pipes and up. So we'll sort of be pushed up all the time. Yeah.
What is the difference in function between the subsurface safety valve and the blowout preventer?
The blowout preventer is placed on top here. So that's the blowout preventer is used until you can get the Christmas tree into place. So you drill the holes, and as you are completing it, then you have a blowout preventer placed on top there, and those are usually like 250 tons or something. So they're really heavy, and they are meant to be heavy enough that when you get if something should happen down here, you would get the entire pressure of the production flow. You would get it straight up, and it would hit the blowout preventer, but it is supposed to be heavy enough and firmly enough in place that it will just stay there. It won't be moved. So basically, you are putting a really heavy lid on top of it. until you are ready to complete the well and place your production equipment, all of your valves and stuff down there. So the blowout preventer is there almost to the end. So when you're doing when you're going to put the Christmas tree down, then you are first lifting the blowout preventer up, and then you are placing the Christmas tree down and stuff. So this one is a bit difficult to see, and again the shadows are not playing along. The part where we have here, there's sort of a loop here, and the text is really difficult to read, but that's a pigging crossover module, because you have something that is sometimes done in the production lines where you send what is called a pig through it in order to clean it, basically, because you will have, as you have production fluid moving through it, there will be almost like oily fats inside the oil, and they get deposited along the inner walls of the production pipes. And if you get too much of this, you will sort of start constricting the cross section of the pipeline. So you have to keep them clean them every now and then. And there's a lot of other stuff also that these pigs do. The most complex of them have a lot of sensory equipment that will sort of give you a detailed view of what's going on with ultrasounds and everything as they pass along the production lines. So this loop part is basically what I'm guessing, since it's a pigging crossover module, is that it's supposed to send it from one production line to another. So it's able to sort of send it through. And these pigs can be really big. I've seen one of them. Imenco had a pigging project. I wasn't a part of it, but I got to see some of it. And it was a bit longer than this table, basically, and it was about this diameter or something. So, and then they have sort of requirements to the design of such a pig, because they have to see what pipeline is it going through, so what kind of bends does it have to be able to make. So a radius of 2 meters, does it have to manage to get through a radius of 2 meters? Then you might have to put in some flexible joints in it or something. So there's a lot of stuff they have to do with those pigs, but they're really cool. If I'm not quite mistaken, the word pig actually comes from the first ones they sent through, I think it was early 50s or something. Then they were basically just a lump with a lot of bristles on it. So it looked like sort of a wild boar. So it was a lot of bristles, looked like the fur of a wild boar. So they put it in, and then it became a pig. So they sent the pig through the pipeline, and after that, it's even though they don't look like that anymore, that's sort of stuck there, that name. And then we also have the control module over here. It's really difficult to see in these old illustrations. But here's one of the Christmas trees. So there you have one Christmas tree, there's another one, and there's another one, and there's another one. So this whole thing is a template with 4 wells. So it has 4 Christmas trees on it. And these going in here, those are control umbilicals that are coming in. So they have been placed here by a vessel, so it's sort of just dropped them down. So it's been laying them along the sea floor, and then when it came close enough here, it would just drop them in sort of a fairly close position. And then an ROV would come down, it would connect a tool up here to the umbilical, and then the tool will sort of pull the umbilical in, and then it will connect in there. So that's been done with both of these. So that's also something they do with pipelines themselves. So even though the pipelines are steel pipes and everything, when you get some length on it, it actually becomes fairly flexible, and then you can do stuff like this and sort of pull it in when you've got long enough pipelines. Then we're going to look at subsea wells. So In general, a subsea well consists of a subsea wellhead, or mudline equipment, as they write here. I'm not quite sure what they mean with the mudline equipment, if they just mean what's placed on top of the sediment on the seafloor. Downhole equipment, which is everything that is placed into the drilled hole. The subsea tree, or the Christmas tree, that's placed on top. The control system. The umbilicals. And the flow lines. And all of this together creates an entire subsea well. So you need the subsea wellhead, which is sort of the area where the drilled hole is exiting the seafloor. So you've got the seafloor and you've got a drilled hole into it. And the subsea wellhead is sort of the base that's been placed here to start your constructions on. And then you have the downhole equipment, which is everything that is placed into the hole here. All of the casings and hangers and safety valves and everything that we saw a bit earlier there. We'll see more of it later on also. All of that is downhole equipment. Then you have the subsea tree, which is placed on top of here again. Then you will have control systems. I'm guessing that the control systems have changed quite a lot since this appendix was made. But the basics are that you have the control systems located somewhere very close to the Christmas tree. Whether it is directly connected to the Christmas tree, or if it's placed just beside of it, or something, it's very close to it. Then you have the umbilicals. They will be coming from if we have a rig or a surface vessel up top. So you will have a umbilical that will come down and be connected to it. And the umbilical will, of course, be connected to both the control system and whatever the control system is controlling. So if it's valves that are going to be opened and closed from the control room on top, they will send signals down to the control module. The control module down here will tell the valve to open or close, and it will use the power it gets through the umbilical to do this, whether it is hydraulic power or electrical power. And then also we have the flow lines, which will be more like basically the pipelines. So some sort of riser system going up, and then the pipeline going into the production valve of the Christmas tree. And you have several ways of drilling a subsea well. You can use the semi-submersible, which we've already looked a bit at. You can use a drilling ship. And as you can see, it has a huge tower in the middle here, and it also has this moon pool, which we talked about last week. Then we talked about lowering large equipment through the moon pool, but here they are actually doing the drilling through the moon pool. So it's, if I'm not quite mistaken, on a drilling ship, the moon pool is quite a bit smaller than on a installation vessel. You also have jack-up drilling units, so if it's not too deep, they will use these jack-up rigs. And basically, these legs can be, for lack of a better word, jacked up, so they can be pulled upwards so that they will stick further up here, leaving the rig as a floating vessel. Then it will be pulled by. I'm not quite sure if they can be self-propelled or if they have to be pulled by other vessels. And then when they get into position, they sort of lower their legs until they hit the sea floor, and then they jack themselves up until they are lifted above the water. So they can start drilling then. But of course, this is limited because they can only reach that deep. They can't really be done. Do anything on deep water. Yeah, the floating, or basically the drilling unit that is drilling, it uses the blowout preventer, the BOP, and places it at the seabed when it's doing this drilling. Some of them, which is specifically the jackup units, some of them actually have the BOP placed topside, so it's on top of the drilling string up top here, which means that if you would have a blowout down in the reservoir moving upwards, it would actually go through the sea floor, of course still inside the drilling line, and it will go all the way up here, and then the blowout preventer would stop it. So instead of stopping it down by the sea floor, it's allowed to move all the way up. So in my view, it's a less safe system because something could happen here. So what if the drilling line bursts or something? So you would have a huge problem. So it's I don't think the jackup rigs are that much used anymore, because I think all of the easy reservoirs in shallow water have mostly been done already. So they've found most of it. Yeah. So to start with, they place a. Just going to see if I have one more. Yeah. They place a temporary guide base on the seafloor. And then they have, as it says there, 4 guidelines, which means just the temporary guide base is a square, so it has a guideline in each corner. And it is placed down on the seafloor. Then they lower the drilling equipment down through the temporary guide base, and they start drilling. So then they actually use a 36-inch bit when they start drilling. So 36 inches, that's pretty massive. It's really huge. So it's you can crawl into that hole without a problem. It's you can fit a person in there. Huh? Yeah, usually. It depends a bit, of course, on the reservoirs and stuff, what dimensions they use, but usually they start off with something around 36 inches, because, as you can see on the next one here, the first casing they put in is a 30-inch casing. And they want some room around there because they are going to fill it with cement. So they want room for the cement to go in there. And they also put down a sort of permanent guide base into onto the temporary guide base. So as you can see, the temporary guide base has these guidelines connected directly to it, and it has a guide rope going between all 4 of them, which is sort of just centering this drilling line that's going down the middle. So that's the function of the guide rope, is just to make sure that the drill line stays in the center of the that it will go through the center of the temporary guide base instead of hitting one of the sides of it. So they send that one through there. Then they lower down the more permanent guide base and put it on top of the temporary. That's why they have them in brackets, temporary and permanent, because it's a base. But it's only guiding temporarily. It's not used for guiding later on, but it's used as a base later on. So the permanent guide base is placed on top of there, and it will have more conventional guidelines that can be detached easily using equipment. Emenco creates a lot of guide wire equipment for such use. Then they continue drilling. So they can continue drilling down there. They had the 30-inch case, and a 26-inch hole is what they're drilling. As you can see here, there is cement along the 30-inch casing, so that it's in place there. And it has, of course, everything that they do up here, it has to be strong enough to withstand all of the pressure that will be coming from the reservoir later on, when they get far enough down that they hit the reservoir. And as you can see, they continue to downsize the drill bit as they go further and further down. So the 26-inch hole needs to be a certain length, and they put in a 20-inch casing in it, and they cement that one also into place to make sure that it's locked in there. My feet to meters conversion isn't all that good, but as you can see, it's 2,000 feet down there. So divided by 3 approximately, you get around the meters that it is. And then they continue on drilling. They put the wellhead on top. No, they don't continue the drilling. They have put the cement in. That was with the wellhead. Then they put the blowout preventer on top, because now they are starting to close in on the reservoir. So now they know that, well, sooner or later now we are going to breach the edge of the reservoir, and then this hole is starting at first a bit slowly to fill, and then as we continue drilling, it's just going to flow in there. So they put down the blowout preventer on top of the wellhead. They put in more casing hangers down here, and they cement things in place. And as you can see, the dimensions are quickly being reduced here. And then you have about 10,000 feet down, so roughly 3,300 meters or something like that down here. So it's pretty deep, this one. So here's a bit more of a view of what's happening up here. So you get the temporary guide base is placed here. You can see the wires that are going up. They are going through everything here. And then you have the permanent guide base has been placed on top of it. These are guideposts, which are used when you are lowering, like the Christmas tree. Can see if I can pull it up back here. It's quite a bit far there. When you're lowering the Christmas tree, you can see they have these sort of small funnels here. So the guide wires will be going through these pipes and funnels. And so that as it moves down on the guide wires, just get all the way back here. As it moves down these guide wires here, it will eventually come down so that the funnels hit these guideposts. And then they've got like an inch or so to go on in diameter there. So they got some room to move around when they are over the guidepost, but they are fairly locked into place. Especially when you have 4 guideposts also. It's not much movement you have going on there. So the last part of the lowering will be pretty fixed in position, so that it will going straight down instead of all over the place with ocean currents and everything. And here you see that they put in pretty many different sizes of casings, and they are suspended from mounts on the inside here. So they put them inside on the top here, and they sort of hang them there. So the casings are just hanging there, and then they pour the cement in so that they fix it into place. There's just an example of what a guidepost looks like, because these some systems have these guideposts permanent, so they're fixed. They are welded into place there. They can't be removed or anything. But many systems actually just have sort of a bucket down here where you can lower down a removable guide post, so you can sort of lock the guide post into place. And this is one of the products that Umbilicals has. So you have the yellow bucket that is placed on the structure. Then you lower down the guide posts, and as it moves into here, you have some locking dogs down here that are pushed inwards as it is lowered down, and as soon as it exits underneath there, the locking dogs fall out again, into place, so that they are kept in place. So even though they are pulling pretty hard on these guide posts, they stay into place because they are locked to this bucket. And then you have up top, you have a release mechanism where you can, by the ROV manipulating a ring up top, so sort of just twisting a ring on the top of the guide post, it then pulls in these locking dogs so that you can remove the entire guide post. So we'll do a break there. And then I think we had this room for the next lecture also, so we'll just stay here.